Good morning. This is Scott Sanford. This morning we have Bill Krantz from University of Nebraska. He's going to be talking about the evaluating energy use for pumping irrigation water. So anyway, I'm going to turn it over to Bill, and we're going to learn about water pumping plants. Thanks.
Thanks, Scott. Good morning, everyone. Wanted to talk about pumping plants and how we might conserve a bit of energy with them this morning. And to start off with, the PowerPoint material will at some point become available to everyone to use later on. I wanted to acknowledge my co-authors. There's been several of us here in Nebraska that have worked on portions of this presentation and some printed materials that we'll share with you later on. Scott mentioned there'll be several parts to this, or a couple parts to what we're talking about, and this just kind of shows, I'm trying to put a perspective on where we might conserve energy related to irrigation systems. And there are some factors that are under our control or the producer's control and some that are not. And across the top banner will be items that the producer can control, and there will be some things that on each side of here that they really are out of their control. So we'll talk about irrigation scheduling and application efficiency at a later time. And basically that controls how many inches of water that a person might pump on an annual basis. And certainly that'll be based upon a number of factors that you see over here on the left that are largely out of the control of the producer, other than the field size here in terms of how much they irrigate. Crop water needs will be on an annual basis that will change. Precipitation is a highly variable kind of item. So anyway, one way to save energy would be to reduce the amount of water that we pump. The other two items are related to the irrigation systems themselves, and we're going to visit in detail about the performance rating box that you see there towards the middle on the right-hand side, and combined with the operating pressure, and we'll talk about that at a later time as well. Go into how much it costs to pump an inch of water out there on the field. And the things that are out of our control here in this regard would be the pumping lift, which is based upon wherever we're getting our water supply from, whether it be from a surface water river, stream, pond, what have you, or pumping from groundwater, and the price of energy, which I'm sure most people would like to have under our control, but certainly it is not. And if you add these factors together, then we have the basis for how much it costs to irrigate a field on an annual basis. Just a little bit of an update here, I think, in terms of the distribution of energy sources that people might be using on the field. This is information off of the 2007 Census on Ag, just for the state of Nebraska. And it wasn't that long ago when diesel and electricity here in Nebraska were largely the same, but because of the increase in fossil fuel prices, as we'll see here in just a little bit, over the last 5 or 6 years or so, we've had a tremendous development of or conversion from various fossil fuels over to the electrical side. In fact, here in Nebraska, there's sometimes a 2- and 3-year waiting period for people to get converted over to electricity with today's prices. So you look at here, and I would guess that in some states there may be more electricity than what we have here, but certainly there are varying numbers here in terms of percentages that you might expect. We look at long-term energy prices, and this goes until 2007. It's from the Department of Energy numbers. And you can kind of see the trends here, and in particular, how electricity is gradually become the less expensive fuel source here for most people. At least in Nebraska, natural gas, if you if the pipeline doesn't flow through your field or pretty darn close to it, you won't have access to the natural gas. And so even though it tends to be less expensive, it's not accessible to very many folks, at least not here in Nebraska. The other thing here is we look at the energy content of fuels in general, and the second column here gives the BTUs that we might expect per unit of fuel source or energy that we have out there. And so you look down through the list and you can see the variation that is there from one fuel source to the other, how many brake horsepower we can expect for those units. And in the middle of this table are some units that we'll come back to later on in terms of the brake horsepower hours per unit of fuel and water horsepower hours per unit of fuel that are involved in Nebraska pumping plant performance criteria. And then the last two columns there will provide then the assumed or the defined efficiency of the motor itself. So you look down through the list, and you know, the electrical motor is the most efficient, but it also requires a bit of that's not considered here in terms of developing the electrical energy itself. And then on the far right, that's what percentage of the 31, or I'm sorry, what percent is converted then to actual work. And in general, these numbers end up being around 75%, 70 to 75%, depending upon what the source of fuel is. So let's look at why maybe this might be important to folks. If we look at an average performance rating here from the Nebraska standard of 80%, which is what we're finding kind of as an average over time here, and we go upward from our average pumping depth in Nebraska, 150 feet. Our average pressure at the pump outlet is 60 psi, and go across. And at $4 per gallon diesel fuel, we're talking about $1,700 to put on an inch of water on a full quarter section center pivot that would irrigate 130 acres. So each time these pivots goes around now, they require quite a bit of funds in terms of the operating cost. And this is just the fuel cost. You look at the overall cost, and it can be double this number to put on an inch of water because of the ownership cost and that sort of thing. So as we look at then the types of systems we might run into out there in the field, certainly there are going to be units in various places in the region. They're going to have centrifugal pumps pumping out of some surface water impoundment. And we'll come back to this in terms of how they function a little bit later on in the video that'll come at the end. And also in Nebraska, we're primarily going to be using deep well turbines here to pump the irrigation water. So if we look at how the centrifugal pump, and this will be in more detail later on, but basically, you know, we got water coming in to the eye or on the left-hand side here, and coming out on the top of these. Most of the time, they're either going to be horizontal, coming out the top of the bowl assembly, or they're going to be straight up coming out of the bowl assembly, depending on the manufacturer of this type of pumps. As we look at an installation, then where this might be, we'd pumping out of some sort of a surface water impoundment or very shallow groundwater, and well, again, we'll come back to that, some of the details of that in a little bit. We're going to have some sort of suction pipe that is going to be submerged in the water supply and to bring water into the eye of the pump that's in the center part here. So we have an intake or suction pipe, distribution pipeline to get it from wherever our pump installation is to our distribution system, whether that be a tow line or a center pivot. Even a furrow system, it really doesn't matter. We're going to have these kinds of components in this system. If we look at the energy required, we're going to do a total dynamic head, and the first one here is the suction lift. And because of gravity and you know, perfect vacuum is essentially equal to our full gravity because of friction losses, and first one thing or another, we can't get the full 29 point whatever feet we might be looking at here. So the maximum here is around 25 feet that we can draw the water up. If we try to do it, and as we get close to that 25 or so feet here, we're going to risk having some cavitation issues on these type of pumps. The other thing is how far are we going to pump the water uphill potentially in this system? So we have an elevation head kind of number. H sub P here is the pressure. So depending upon whether we're running a low pressure center pivot or a high pressure volume gun somewhere, that number is going to vary. And lastly, we're going to have some friction loss in this pipeline. And basically then we add all of these up to get the total dynamic head. And this is the number we'll come back to in terms of calculating the water horsepower output of a pump and the brake horsepower required to do the work that we want the system to do. So let's look at the deep well turbine. Again, we've got some similar components. But as we look at this picture here, we're talking about pumping out of a groundwater supply, and typically we're going to have a well casing here that's surrounded by a gravel pack. As we look at these, and the pump impeller or the pump column is going to be hung down below a pump base that's on the top up here, and depending on how deep the water is, this pipe can be several hundred feet long in some cases. There's a drive shaft that goes right down through the center of this pump column here. You can kind of almost see at least the depiction of it sticking out the bottom where the screen is, that drives this pump from the surface. And so we provide some sort of power supply at the top here above ground that's going to drive this pump and provide energy to it to move the water from wherever it is in the groundwater to the soil surface and through our irrigation system. Typically, these days, these pumps, our wells are installed so that they're right down close to the bedrock. In some cases, they actually drill into it a bit. So they know that the aquifer and the pump and well are fully penetrating. The last thing I'll say is that we have a well screen down at the bottom of this particular well, and generally that's not something that goes full depth of the aquifer, but might be somewhere 1/4 to 1/3 of the depth of the aquifer is where the screen is, and this is going to be some sort of a slotted piece of material that allows water to come into the pump column or the well column. So let's look at a bit of terminology here as we look at the turbine pumps. We're going to look in a little more detail. I'm going to be talking about stages and bowls and that sort of thing as we go along here. As we talk about a stage, basically that's the one unit here, or one impeller that includes the bowl, the impeller, and the surrounding material, bowl assembly that is bolted together to make up a pump that would look like this. You see the center shaft or the line shaft coming down through the center of this particular system. The bowl is basically the metal shroud that goes around the outside of the impeller and provides areas where water can move upward through the system. And the impeller here that we'll talk a bit more about is usually a brass or can be porcelain coated material here to work on this. Now, let's just look at a bit of design here for just a short period and see how this might come into play. But we have a 800 gallon per minute system requirement out there, and that requires 216 feet ahead, and we'll come back to how we get these numbers here in a little bit. And basically, if we have an impeller that's going to produce some sort of feet of head per stage. And so how do we do this? Then we have 216 foot requirement and 34 feet output. Basically we're going to put these in series. And so if you notice the drawings up till now, there's been more than one pump bowl assembly involved in this. And we're going to select then these impellers to do what we want to do. Just to give you an idea, and again, we'll have some more pictures of these later, but we have basically open impeller systems where the blades are exposed to the water coming into the impellers. And we also have semi-enclosed or enclosed impellers that have a bit of a shroud around the bottom, and I'll show you pictures of these here in just a minute. But basically then we're going to put these in series, we put one of these on top of the other or stack them to make up a pump. And depending upon what the total head requirements are and the flow rate, will determine how many. I guess the flow rate's not involved, but the total head requirement will determine how many of these impellers are stacked one on top of the other. So here's the curve that I got the 34 feet of performance for the pump. And not to say that this is going to be the best pump for this installation, but if we look at this, we have 216 feet, and we go up from 800 gallons a minute and go across. Basically we're going to find that where I got the 34 feet of head per stage from. And if we then divide the 216 feet of total by 34, that says we're going to need 6.35 stages or impellers to provide enough pressure to do what we want to do. Now, in the top middle of these curves, there's typically, or somewhere on the page at least, there's some information, and I've got it kind of circled here, that basically is an adjustment in the operating efficiency here that will, depending upon how many impellers you have stacked one on top of the other, you make an adjustment. So in this case, I know this is hard for you to read, but if we have 4 stages or 4 impellers stacked one on top of the other, there's no adjustment. If we only have 1 impeller here, we subtract 3 from the operating efficiency. And these numbers that you see in the circles here are actually the operating efficiency that we expect this pump to be. And the idea here is to be very close to the maximum or very close to the 83 in this particular case. And so we're not too far off of the high point of this particular pump impeller. So how we do that then is that we create what's referred to as a multiple stage pump by stacking them one on top of the other. And the bottom line becomes, well, how do we get the last 0.35? And as we look at these then, there's other information on these particular design sheets. In this case, there's 1,750 RPM as the standard operating. If we're going to run this system, we can run it at other RPM, and we will then shift these curves downward or upward depending upon the RPM that we select. And so we might be able to pick up that last 0.35 simply by increasing the RPM just as slightly, and certainly it won't take very much. The other thing that you notice here is that there's 3 curves on this graph, and they represent different diameters of impellers. And it's not uncommon for a well to have more than 1 impeller diameter in the system. So in this case, we might have 5 impellers that are the full 7.96 inch diameter, and we may have 2 that are 7.26 to get that the total head requirement supplied by the particular pump. And so there are a number of things we can do in terms of the design, and you run into this potentially out in the field, and you more or less have to know that these things are going on. Now, the other thing is with the turbines, typically we're going to have 2 types of installations, and that is you have a hollow shaft electric motor here on the right that is direct coupled to the line shaft of the pump and drives from that perspective. The other way, and depending on where you are, will be some sort of internal combustion engine, whether that's natural gas or propane or diesel, and more recently ethanol and some mixed flow kinds of things that are connected to the right-angle gear drive here by a PTO shaft on the engine that supply the water, and again the drive shaft then or the line shaft goes down through the center. So those are the most common sorts of arrangements for deep well turbines that you're going to run into out in the field as you work with producers. Now, again, here just kind of a pictorial depiction of how the water would run through here, and each one of these impellers that you see are on this particular page is going to provide the same amount of energy per stage, and the water as it comes into the eye at the bottom here will then, by centrifugal force, be moved upward into the next bowl assembly or out towards the surface. Now, The reason why these sorts of things come into play, there's a couple of reasons. One is they just had some improper selection of equipment to begin with. The other is wear and tear on the machinery. And these are mechanical pieces of equipment, of course. In this case, we've got brass riding on another metal. And on the one on the left, the enclosed impeller, you can see the shroud that I was talking about on the bottom of this, and the impellers are up inside. You can see the ends of the flutes on this. Water comes in from the bottom and is the centrifugal force, but you can see on this portion right here some wear and tear on this impeller. And so when this gets to this wear starts to happen, we have some things going on inside the bowl assembly that I'll talk about. The other thing is this is an open impeller, and you can see here that the tops of these impeller blades have been ground off. And in this case, this impeller was improperly adjusted down too far, and so we had metal running on metal, and we're gradually wearing these blades off. And so between these two, we're going to have some differences in how we're able to make some adjustments. But what ends up happening then with that worn seal that goes in there is that some of the water is actually leaks past and goes back down into the lower bowl assembly, and we have to repump it and repressurize it again. And when this happens is where the extra energy is being used. At least that's one part of it. If it's poorly designed from the beginning, then we've got other issues. So this adjustment is the key, and pump installers oftentimes will tell us that their initial installation is to just barely get this seal established here because they know the wear is going to happen, and the idea is then that they would the producer would call them and they'd come out and adjust this downward. So this key is critical here to maintain this, and through adjustment this can be reestablished. Now at some point you can't adjust this further down, and that's where we run into situations. If the bowl assembly was adjusted all the way to the bottom as far as it could go and operate all right from the beginning, then there's really nothing the well driller can do with the adjustment on these. Now, let's take a look at then what we might expect in terms of aquifers, because we're going to run into some situations that are somewhat different, and you might find some different sorts of things out in the field. Most of the state of Nebraska has unconfined aquifers, which means that the water comes down through the surface and goes directly into the aquifer itself. In other parts of the country, we'll have other kinds of systems, and I'll talk a little bit about them here in just a second. But as we start pumping water out of these, what's going to end up happening is that we develop a cone of depression where a portion of the aquifer is actually dewatered, and there's an energy gradient that you see the shape of this curved water surface coming down, and by virtue of developing this gradient, we're drawing water in through the screen that's at the bottom of this particular system. And so in this case, we're actually removing water from this area up that was formerly in the aquifer system, or the water table went all the way up to this dotted line. And we start off with this, I forgot to mention the static water level here on the left. Now, in points east of Nebraska and in some parts of Nebraska as well, we have pumping installations that are in what we refer to as a confined aquifer. And basically what that means is we've got bedrock down at the bottom, and we've also have some sort of impermeable layer that makes up the surface of the aquifer system. Now, because the upper level is there, it creates a situation that depending on where the water, source water is, it can be miles and miles away and at a much higher elevation. I'm showing a higher elevation here in this particular case. You can see how the static water level is up in the well above where you see the blue in the aquifer system down below. And this is kind of an artesian kind of effect, but it basically means that this water is under pressure. Now, if we look at the same scenario we've looked at before and we pump water off, theoretically, we're not dewatering the aquifer system at all. And depending upon what material is in this aquifer down below, we actually get a movement or subsidence, compaction of the aquifer material. And you noticed how I moved the semi-impermeable layer down, but basically the whole profile moves down. And in some parts of the country, this has meant 17 to 20 feet of subsidence in areas that in California where they've dewatered confined aquifers over time. And so the other part of this is that we end up having oftentimes quite a bit of drawdown in the well that would be in other words, the material out here in the aquifer may not be as permeable as it would be in a unconfined aquifer system. So we look at then this and how we might look at this. The total head here, our total dynamic head, is the lift. How far are we lifting this water to the surface? And then the outlet pressure here times 2.31. This is the conversion factor for how many psi there is per foot of water depth. And lastly, in this case, it's fairly minor, and some people include it and some people don't in terms of how we look at this. But basically, depending on how long the pipe is from the aquifer or the pump column is, we're going to have some friction loss in this pipe to get it to the surface. And so, again, some people utilize that number to be thorough. So how will we do the calculations? Let's say we've got a situation that you see with the red numbers here, outlet pressure of 50 psi, 800 gallon a minute, and we're pumping from 100 foot deep. To do the water horsepower, this is the work that we're going to get out of our pump. We have the pressure. This is the total dynamic head that we just talked about, and the flow rate divided by 3960. And if we put the numbers from up above in here, that would say that it requires 44 water horsepower to do the work that we want to do. Now, the question comes up is where does this 3960 come from? And basically, if you multiply these numbers, the P times 2.31 plus L times Q, you come up with units of feet, gallons per minute. So to convert those numbers to horsepower, there's 33,000 thereabouts foot-pounds per minute in 1 horsepower. And then 1 gallon of water at specific gravity of 1 weighs 8.33 pounds. So if you take 33,000 divided by 8.33, you get 3960 or 3962, depending on what numbers you actually round off there. That's one way of coming up with the 3960, but you can also just directly multiply the feet gallons per minute by 8.33 pounds per gallon, and then divide 33,000 foot-pounds per horsepower, and you'll get the same sort of response. So that's where the 3960 comes from. So we look at the brake horsepower. Then the only thing we don't have before is the efficiency of the pump. And in our example curve, as I showed you a little bit ago, we were operating at 82%, so I'm using 0.82 here in the bottom of this equation. And that says that we should have a minimum of 55 brake horsepower for this system to operate. Now, when we take a look at the performance of irrigation pumping plants in this regard, one of the things that came into play a long time ago, around 1958, 59 time frame, there was a professor at the University of Nebraska wanted to, and probably elsewhere, wanted to test and compare pumping plants that were fueled by different energy sources. And so he developed this performance criteria that would basically end up with a performance rating, or in this case, the Nebraska pumping plant performance criteria that basically then, this gives you a performance rating. The criteria is here and allows us then to come up with a number that if we have a performance rating of 80% for a system powered by diesel fuel, we could compare that to 80% of one that is supplied by electricity, let's say. So where did they come up with this, the performance criteria? Well, over the years, several states have been involved with this, and I'm not going to show you all the data here this morning, but in Nebraska, the the tests were based upon a whole bunch of tests out in the field of pumping plants, and then information from the Nebraska Tractor Test Lab. And basically this performance criteria is then how much work can we reasonably expect from the pumping plant as a unit, pump, engine, and motor kind of thing, and to produce per energy or unit of energy consumed. And then as we look at then with an average performance rating here, testing 165 pumps, we had about 75% or 77% of the performance criteria later on. So basically over time, in those tests that were conducted in the early 80s, we were using about 30% more energy than what we needed to get the job done. Now, over time, there's been a number of things happen, but these criteria have been there for quite some time. As we look at them, this column here, the energy added for water per energy use rate, or water horsepower per unit of fuel. You see the numbers here are 12.5, 8.66, likewise down to 0.885 for electricity. These are the performance criteria for different energy types. The one for propane has been in existence since 1959. So we're in the process of doing some work to update those, and I'll share a little bit more about that here in a second. But just wanted them to point out here in the bottom, 15% of those the tests that were run in 1980, when the diesel fuel criteria was updated, 15% of them were at 100% or higher of the performance criteria. So it's a reasonable thing. It just takes some good design and maintenance work to get the job done. Now, we thought maybe there would be some improvement over time, but here's some work that was done by Tom Shear and his colleagues at North Dakota State University, published in an ASABE article in 2000, where they looked at pumping plants that supplied water to different types of irrigation systems. And on the left-hand side here, you see the performance rating, the categories, greater than 90%, 80 to 89, 70 to 79, less than 70. Now, the numbers here are percentages of the systems that were tested, and you can see that about 50% were above 80% of the performance criteria, 28% for center pivots at least, 28% were above 90. There were some that were above 100%, but you also see that about half of them were less than 80% of the performance criteria, which would basically lend some the notion that maybe things haven't improved all that much. We look under the surface irrigation section here. You notice that the numbers are, quite a few of them are less than the 70%. In these systems, they were pumping water out of canals and groundwater that had sand in them, and first one thing another, a little bit harder for pumps to function over time and maintain high operating efficiencies. And so these kind of units are, I guess, maybe most in need of improvement here in terms of our maintenance work over time. Okay, I mentioned we're doing some work, and we've got a master's student at Nebraska working on updating the performance criteria, and we're doing that based upon some testing of the engines in the lab, utilizing information from the tractor test as well, and then we're going to be doing some intensive measurement for 24 to 48-hour periods of various energy types this coming summer. So we're in the process of trying to, for each of the energy types, update that performance criteria for the new types of engines, Tier 3, Tier 4 engines now that are required for people to purchase. Now, so once we have the system out there, producers can do some things for preliminary to determine whether they are using extra energy, and so as we work with producers, we can do somewhat similar things if we have the records. We can to work with them. You know, basically, we're going to use the energy use records or what they paid for on an annual basis. We're going to look at the pump characteristics in terms of what type of pump it is, how it's operating, pressure, flow rate, those kinds of things, and we're going to use the pumping plant performance criteria or standard here to make some calculations. The first thing is is to do the things out in the field. But what it's going to allow us to do is look at being able to estimate how much energy we're going to be able to save if we bring this performance or the pump up to the performance criteria. And then compute how much we can invest. So we're going to go through a little example here this morning, and there'll be handout material available that goes through this material as well. But let's have an example where we have 125 feet of lift, 50 psi at the pump, and we have a field size of 130 acres. Average application is 13.5 inches. And let's say that the fuel used by this system last summer was 5,500 gallons of diesel fuel, and I'm using a more current fuel cost than that would be. But let's start out with these kinds of things. And I guess, Scott, I was supposed to maybe have some pauses here if there are questions. Are there any out there that I should deal with now before I go on with this? Okay, I'm not hearing anything, so I'll go on. So the first thing is that we've got a table here in the handout material. Will be table 2, and basically we have across the top we have operating or discharge pressure at the pump outlet, and down the left-hand side we have pumping lift. And so in our example, 50 psi at the outlet and 125 feet of lift, that says that this table indicates that we should use 2.19 gallons of diesel fuel to pump an acre inch of water. We'll just add that to our little table of things here, 2.19 gallons. So the energy cost savings overall then is going to be how many acre inches did we apply? We take the 130 times 13.5, 1,755 acre inches. Here we have the 2.19 times that 1,755. That says we should be able to pump that water for 3,843 gallons of diesel fuel, but we're using 5,500. So the performance rating then, basically you can do it this way. How many gallons of diesel fuel should I be able to do it with, divided by how much I actually used? In this case, that gives us a 70% performance rating. So how much energy can we save? If you do the math there, 5,500 minus 3,843, 1,657 gallons we could save on an annual basis if we were to make improvements in the system and bring it up to the performance criteria. At $4 per gallon, that's $6,600 roughly per year that we could save. So the question is, though, how much can I afford to spend a day? Because we may take more than that $6,000 or $6,600 to do everything that needs to be done. And it's surprising once you start pulling deep wells how much it does cost. So to make that calculation, we use a series present worth factor to convert an annual payment to a one-time fixed payment up front. And let's say that we have the 9% interest that we started off with in the 5-year repayment period. That says our series present worth factor is 3.89, and that would come out of table 6. So multiplying here, we end up that we could spend $25,000, almost $800 to make repairs and improvements today and pay for it with the energy savings over a period of time. And certainly as the price of fuel goes up, these numbers go up as well. Now, that was for diesel fuel, and certainly you're not going to run into all diesel fuel systems, and so in our handout material we've got a conversion factor, a multiplier, that you take the result from diesel fuel and just multiply it by these numbers. You'll get the result for each specific energy source. So if we wanted to convert to electricity, or we have an electrical number, we take the diesel fuel number and multiply it by 14.12. So that 2.19 gallons per hour times 14.12 would be how many kilowatt hours we should expect to use for that system. Now, if we look at another kind of an example here, if we have a 12-inch annual application on that same 130 acres, but a little bit deeper depth to water or pumping water level, 150 feet, 60 psi at the outlet, and we're at the performance criteria. And when we look at the effect of fuel cost on these numbers, diesel fuel, for instance, got a range of $3.50 to $5 per gallon here. And down the left-hand side, we've got electrical prices from 7 cents to 10 cents, and then at the very bottom, there's a 30-cent number there. And you look at the reason why people are converting to electricity, the numbers that are in these columns are all savings that would be, or lower cost that would be for an electrical system today at those prices. And at the very bottom, the bottom line is there, as you go across, as the diesel fuel price goes up, you can see as we go from negative numbers to positive numbers, the break here somewhere in the $4.25 a gallon maybe, but it takes 30 cents per kilowatt hour electricity to get to that point. Okay, let's say you want to do this on a per hour basis, then we just take our flow rate and divide it by 453 basically, and you end up with the numbers that are in this table 5 that'll be in the handout material, and that'll convert it to acre inches per hour. So we'll also have a worksheet and a website that I'll give you here in just a minute. But basically then we've got this, and it allows you to put the numbers into the chart and figure out what the performance rating is at the very bottom here. Also, Tom Dorn, and one of our extension educators in Nebraska, has a website that's here on this particular image, where you can look at not only the pumping cost but also the ownership cost. And over in the lower right-hand corner, it summarizes then the total cost of pumping an inch of water on an acre of land. And so just some additional kinds of support materials that are out there, and other states have similar sorts of programs, so this is not by any means the only one. Now, we run into on occasion situations like this, and where this particular unit was, the pressure at the pump discharge was 75 to 80 psi. The pump and the pivot were on the top of a hill. The center pivot was equipped with 25 psi regulators. And so the way this particular system was being operated caused the pump efficiency to be 56%, which is approximately 25% lower than what it should have been for this type of unit. So in this case, the pumping plant was not the issue, the operator was. And so we run into some of those situations, and if we run into them when we're working with folks, I guess we need to counsel them to do that. So what's next? And so basically our recommendation is that if it looks like there's some energy that can be saved and it's significant, that they have a detailed pumping plant test run. And so, Brian, if you could hook us up with the video at this time, please.
As the price of energy increases, the cost of applying an inch of water makes it more critical that irrigation pumping plants operate at near optimum efficiency. Thousands of dollars can be saved each year by making sure that the current fuel use rate is appropriate for the amount of work being produced by the pumping plant. This video was created to discuss how to test an irrigation pumping plant and determine whether energy can be saved. An irrigation pumping plant consists of two main components, the irrigation pump and the power supply. Two types of irrigation pumps are used to deliver water from the water source to the irrigation water distribution system. That's centrifugal pumps and deep well turbine pumps. When the water source is a surface water pond, river, or irrigation canal, centrifugal pumps are often used to deliver water through the farm irrigation systems. Centrifugal pumps operate by developing a partial vacuum at the impeller inlet or eye of the impeller that causes the atmospheric pressure to force the water into the pump. As the water passes through the impeller, energy provided by the pump power supply is added to the water via centrifugal force. Thus, water exits the pump impeller at a positive pressure determined by the overall shape, diameter, and rotational speed of the impeller. Depending on the use of the pump, impeller rotational speeds can vary from 1760 to over 3500 revolutions per minute. The second style of pump is commonly referred to as the deep well vertical turbine. This type of pump places the pump impellers near the bottom of the well or sump. Energy is added to the water passing through the impeller in a manner similar to the centrifugal pump. However, the power supply can be a vertical steel shaft that reaches from the Earth's surface downward through all of the pump impellers, or an electric motor placed directly above the impellers. Individual pump impellers are contained in a pump bowl assembly or stage and are normally capable of adding 50 to 60 feet of head energy per impeller. Regardless of the type of pump, to determine how efficiently the pumping plant is operating requires measuring 4 different variables. Those variables are pump outlet pressure, pump flow rate, pumping water level, and energy consumption rate. The pump outlet pressure, flow rate, and pumping water level combine to determine how much work is being produced by the pump, or the water horsepower hours. The water horsepower hours produced is compared to the amount of energy consumed to determine the overall operating efficiency of the pumping plant. The first item that should be addressed is to obtain information about the pump installation. The type and number of pump impellers and the depth of the pump should be identified before initiating the test. One key component of the test is to determine how much head or pressure the pump is producing. The output pressure measured during the test will be compared to the design pressure to determine if the pump is operating on the initial pump characteristic curve. The type of impeller will determine whether adjustment of the impellers is possible. The depth of the pump will prevent the operator from lowering the pumping water level sensor too far into the well bore. To record the pump outlet pressure, the pressure gauge or transducer should be positioned near the pump outlet and at the midpoint in the pipe in the vertical direction. Normally, there is an access port located near the pump outlet for a freshwater faucet that can be used to record the pump outlet pressure. Correct placement of the flow meter is key to measuring the pump flow rate accurately. Regardless whether an impeller type, prop type, or ultrasonic meter is used, there should be a minimum length of pipeline upstream and downstream of the meter. This minimum distance should be without obstructions like valves, pipeline outlets, elbows, or pipeline diameter changes. To record the flow rate accurately, there should be a minimum of at least 10 pipe diameters upstream of the meter and 5 pipeline diameters downstream of the meter. So if the pipeline is 7 3/4 inches in diameter, the minimum distance upstream is 78 inches and a minimum of 39 inches downstream. Research conducted in Nebraska found that placing the meter less than 5 pipe diameters downstream from obstructions resulted in a measurement error greater than 19% due to the additional turbulence in the pipeline. In some cases, it is necessary to place the meter on the pivot pipeline or riser pipe in order to get the desired length of pipeline upstream from the meter. One last consideration when measuring the pump flow rate is to ensure that the pipeline is flowing full. The calibration curves for all water meters are based on full pipe flow. If the outlet pressure is low and the pipeline is positioned in a downward trajectory, the very top of the pipeline may be filled with air. In these cases, a pipeline apparatus shaped like an inverted U or some other means of ensuring a full pipeline flow must be employed. Before starting the pump, it is good to update the static water level in the well. Water levels are measured using electric sounders, pressure transducers, and air bubble pressure methods. Access to the well bore is necessary to make this measurement. Most pump bases are equipped with access ports that require a threaded plug to be removed. Each measuring device should be equipped with a weight at the end to ensure the sensor tip is hanging in a vertical direction. If an electric sounder is used, lower the cable into the access port and gradually release the cable into the well bore cavity between the pump column and the well column. Since the pump pump column consists of a series of pipeline sections that are about 10 feet long, and each pipe joint has a flange fitting. The cable may not pass by these fittings easily. Thus, care should be taken to ensure that the sounder cable does not get hung up on the flange by periodically raising and lowering the cable. When the cable comes into contact with the water or an oil, an electrical circuit is completed, causing the meter needle to respond. Low millivolt readings are typically oil, while high millivolt readings are water. Record information about the power supply, including the make, model, and horsepower rating of the engine or electric motor. Obtain the performance curve for the motor or engine for use in comparing against the field test data. Where possible, install a torque meter onto the power takeoff shaft to record the energy being supplied by the power supply. Depending on the type of power supply, preparations are necessary to record the fuel consumption on diesel, natural gas, propane, and gasoline or ethanol-powered pumps. An electronic scale can be used to measure the weight of the fuel used per unit time and convert to gallons per hour using standard conversion factors. Natural gas use must be recorded, though, using a meter specifically designed for natural gas. To determine the fuel rate use, measurements of weight or gas flow rate may be recorded over a period of time using a stopwatch or clock to determine the duration of time between recording times. For electric motors, energy use is measured using a digital meter used for power company billing purposes. Some meters can be monitored using a handheld meter reading device, but the most common way to establish the electricity use is to monitor the three-part bar in the middle left-hand side of the meter. Based on the multiplier incorporated into the meter, each time the bar goes across from left to right is equal to a standard kilowatt power use. Accurate pump tests require the pumping water level, flow rate, and outlet pressure have been stabilized by operating the system for at least 20 to 30 minutes prior to initiating the test. This ensures the power requirements should be consistent over the duration of the test. Once the pumping information has been stabilized, the test can begin. One test procedure is to record each measurement on 5-minute time intervals for 30 minutes. Thus, at time equal to 0, 5, 10, 15, 20, 25, and 30 minutes, record measurements of pump outlet pressure and flow rate, pumping water level, fuel use, and engine speed. Record these measurements on a data sheet for future reference, paying attention to how much each value changes from one reading time to the next. Pump speed is measured using a handheld tachometer or a proximity sensor mounted to monitor the drive shaft speed. Comparison of the fuel use rate of the power supply to the work produced allows the tester to determine the overall operating performance. Once the data collection is completed, the calculations can begin. Calculations can be entered into a spreadsheet or other calculation software that includes equations for determining the operating performance during each time interval and an overall average performance. Dividing the performance by the Nebraska Pumping Plant Performance Criteria will help determine whether extra energy is being used to pump the water. Including the cost of fuel allows the test personnel to determine how much the producer can invest to bring the pumping plant up to the performance criteria. The last component of the test involves comparing the current operating point of the pump with the original pump characteristic curve. Likewise, the brake horsepower and fuel consumption rate of the power supply should be compared with the published literature to ensure that it is operating efficiently. It is strongly suggested that producers employ a firm with trained personnel to conduct a pumping plant test. In many cases, a local well drilling company can perform the test and make the necessary improvements. This ensures that the appropriate testing equipment and testing procedure is used to determine the current operating performance of the pumping plant. Once the pumping plant test information has been summarized, it is up to the producer to record some of the operating conditions in the future. By doing so, subtle changes in performance can be documented until such time as repairs are justified.
In the video, right? So just kind of in summary here then this morning, the performance criteria provides a means of comparing the different energy sources that we talked about here this morning. And certainly one way to work with producers to help is to get them to look at recording their information from the field and utilizing readings of, in particular, the fuel use, the operating outlet pressure of their system, and if they've got the pumping water level, they can do that as well. In a lot of cases, the pumping water level doesn't change all that much over time, at least not from year to year. And so we can get some of that information and compare it from one year to the next to see how well they're doing. We can utilize then the total energy cost or savings and multiply by a present work factor to get how much energy they could save. And then we've got software that will allow them to make some estimations. And finally, I think the bottom line is that we really should have technically trained individuals do the adjustments and do a pumping plant test of their system to verify where the issue might be. The pump test will provide that kind of information and help with the final adjustment. So those are kind of the comments I wanted to share with you this morning, and we can try to deal with questions if there's some out there.